All right, welcome. In this video, we're going to be talking about justifying our answers on improper integrals. And specifically, I'm going to be answering the question you might have, why did I get very little credit on this question, even though I got the answer right? Okay, so I think the first thing I need to do is remind you about the fundamental theorem of calculus, which says that if f prime is a continuous function on the closed interval a to b, then the integral from a to b of f prime of x dx is f of b minus f of a. We take the antiderivative, plug in the balance, and subtract. Okay, we're familiar with this. So, bring in an improper integral like y equals 1 over x squared. And this is where I'm going to show you what's going wrong here. If we go and we're just interested in the amount of area under the graph between -1 and 1, just set up an integral and just proceed as if everything is normal, find an antiderivative, plug in the balance and subtract, we'll see that it's equal to -2. And that's not very believable because if it's going to be finite, what we saw in the improper integral lesson, what we know about graphs above the x-axis, that hadn't changed. We would expect this to be a positive number. So it's like something's going on here, something irregular. And really the issue is that this all goes back to the idea of if f prime is continuous, which for the graph of y equals 1 over x squared, it clearly is not. Okay, the integrand was not continuous on the entire closed interval. It was very discontinuous at x equals 0. It had that vertical asymptote. What I want to do is actually draw you a picture of the graph of the antiderivative, though. You probably thought about the graph of y equals -1 over x before, maybe not recently, but at some point. If we look at the graph of the antiderivative, yes, okay, this is up here at y equals 1, and this is down here at y equals -1. If we just look at the movement of the point, yes, the point went down by 2, but that's ignoring what happened at the discontinuity. And if we think about what actually happened to this function's antiderivative, the antiderivative increased a whole lot. And then after 0, it actually increased even more. And so we'd say it increased a huge amount, an infinite amount. And that's why there's an infinite amount of area under the graph of y equals 1 over x squared. But we have to be careful about these points of discontinuity. And that's why we said when we were learning about improper integrals that if we had a discontinuity, an infinite discontinuity in the interior of our region of integration, we had to split this integral up into two separate pieces. And that was what I was showing you with the movement of the point earlier, is that from -1 to 0, okay, the antiderivative of x to the -2 is increasing by an arbitrarily large amount. Okay, that's why the integral diverges. Each of these integrals could be shown to diverge, and that's why the whole total was infinite, and definitely not -2. So on a problem like this, which is the one you're probably looking at, I did x to the -4/5 for the sake of this example because on the two different quizzes, like -2/3 and -3/4, so I'll do -4/5 and it'll work out exactly the same. Okay, but I don't want to be seen as favoring anybody's quiz or disfavoring anybody else's. All right, so the issue is we can't use the fundamental theorem on this integral from 0 to 1 of x to the -4/5 dx because of the vertical asymptote at x equals 0. This function x to the -4/5 is not continuous on the entire interval 0 to 1, right? That 0 is what's troublesome. And what we learned in the lesson about improper integrals is that in the event that we have an infinite discontinuity, we can take the limit of the definite integral as one of the bounds approaches that, and that is how we're going to work around. But we can't just use the fundamental theorem of calculus, right? Because that only works when the integrand is continuous at all times. So, how we actually solve this is very similar. We proceed as usual, add 1 to the power, divide by the new power. Let x run from 0 to 1, but still, x equals 0 is the troublesome amount. And maybe you're getting, you're seeing what I'm getting at here. You're going to plug in like usual here, but we can't just plug in 0, right? What we have to do is take the limit of the antiderivative, and that's why you got basically no credit. You got credit for the antiderivative work that you did, but then you got credit for nothing else because, and this is the way it is in the free response in AP Calculus, we cannot be getting any credit on an improper integral question if we don't use a limit. I'm not asking you to do anything crazy here. I'm just saying take the antiderivative, make that the argument of your limit, let the x approach whatever x value is causing the integral to be improper in the first place, and then evaluate the limit. Now, if x is not approaching a infinity or negative infinity, what we're going to do, we're just going to plug in that number. So we're just plugging in 0. 0 to the 1/5 power is the fifth root of 0. That is 0. All of this is equaling 5. Okay, but that limit is so crucial. That's probably why you didn't get the credit that you were hoping to get on this problem. Okay, and that's it. It really didn't go much farther than that. I think that's all I've got to say about this. This is exactly the answer to your question. This is why you didn't get the credit you were hoping for. This is just me really doubling down and really emphasizing that even when it might look like you don't need to transform to a limit, if it's an improper integral and we want to get credit, which I know we do, we gotta transform this thing into a limit. And if we don't, then we're risking not getting credit. So that's all for this video. Thanks for watching.